Not so. It's the smallest one. Then I ask you a question now. Now in the routing path direction. How many incoming interfaces are there? Okay. There are 3. They are the loopback ports on this device. This interface. And this interface. So the minimum interface bandwidth of this link. It is the inbound direction of routing transmission. The one with the smallest interface bandwidth. So we will compare the 3 interfaces. Which interface has the smallest bandwidth? Then we need to look at the bandwidth of these 3 interfaces separately. First let's look at our 4. Just check the information of loopback 0 here. Show interface loopback 0. Let's take a look at some of its details. Here we can see its bandwidth. Bandwidth is called BW. This is for our 4. I'll take a screenshot of it and put it here. We'll make a comparison later. Then after watching our 4, we have to watch our 2. 01 interface of our 2. So we go into our 2 here. Show interface E01. Then we can take a screenshot here. Let's see its bandwidth. Its bandwidth is relatively small. Only 10,000. Actually, it doesn't matter if we watch our 1 or not. Because the essence of our 1 and our 2 is the same. Because the interface is the default interface. We did not configure anything. But let's see. Left is 00. Check it out. Here we also take a screenshot of it. See here that the bandwidth is 10,000. So far we have identified all 3 interfaces. This is the far left. This is for our 2. This is the loopback port of our 4. Then please. What is the minimum link bandwidth now? It's here. Is 8 million. We compare the 3 interfaces separately. The 2 on the left are definitely smaller. So the minimum bandwidth is now 10,000. In a moment, we can directly bring it into the formula to calculate. Next we look at the next parameter. Sum of link delays. When data is being transferred. Loopback. Physical interface. Physical interface. These 3 interfaces. Then it refers to this 4.4.4.4 route. Come in through this loopback. Go to our 4. Then all these. In the direction of transmission. The sum of the delays of the incoming interfaces of all devices. Delay in this position. It's the DLY behind. 4R4. It's 5,000 here. The right interfaces of R2 and R1 are both 1,000. It's called delay. Then the sum of the link delays is now. That is. The sum of the 3 interfaces now. Should be 7,000. So now the sum of the link delays is 7,000. Let's do the math. In fact, this formula has already been calculated. First divide 10 to the 7th power by 10 to the 4th power. It must be 10 to the 3rd power. This is 1,000. Then 7,000 divided by 10 is 700. 1,000 plus 700 is 1,700. Then multiply 1,700 by 256. Equal to 435,200. We've actually figured out the value now. This is the 435,200 we just saw. Let's go back to this picture. That means now. This line is actually 435,200. So let's now look at our needs. Make our 3 a viable successor router. Then it means that our 3 is now 4.4.4.4. This paragraph is less than 435,200. This value cannot be changed casually. We can use this formula. Let's see where it can be modified. The only variable parameters are these 2. Minimum interface bandwidth of the link. And the sum of link delays. We can change these 2 variables. If we wish to make this result smaller, I can increase the minimum interface bandwidth of this link. Because it is a divisor. The larger the value here, the calculated value is smaller. Second, this is a dividend. I make the link delay smaller. The total value becomes smaller. So we can actually increase the minimum interface bandwidth of the link and reduce the sum of link delays. These two values can be modified. And in EIGRP, we do make changes like this. Usually, if running EIGRP alone, you can modify it between the two. In fact, just modify a logical parameter. It doesn't matter. It only affects route learning and selection via EIGRP. It does not affect the actual rate of the interface. When everyone understands the interface rate, always feel like I changed this. The interface speed is changed. Not like this. For example, by default this is a 10M interface. You change it to 1000 megabytes. It's not a gigabit port either. We just modify it logically. Affect its routing. But in fact, there is no way to really change the physical bandwidth of its interface throughout the NA phase. If we change, both parameters will be changed. EIGRP can interoperate with other routing protocols in the later stage. In the future, multiple protocols running on a network. If modified, we usually change the delay. But if only running EIGRP, then bandwidth and latency can be changed. Because sometimes if you change the bandwidth, may affect other agreements. So we usually change the delay. But if only EIGRP, both parameters can be changed. This is very common. Then when we modify, we can make it bigger. You can reduce the parameter on the right. But this is not casually changed and does not need to calculate. We have a reference object and modifying. For now, R2 is called the successor router. Then the distance from R2 to 4.4.4.4. It must be less than the distance from R1 to 4.4.4.4. That is, as the main line, the advertised distance must be less than the feasible distance. We now want this paragraph to be smaller than this paragraph. The distance from R2 to 4.4.4.4 is smaller than the above paragraph. I hope now. The distance from R3 to 4.4.4.4 is also smaller than the above section. Then I just need put the distance from R3 to 4.4.4.4. Change to the same distance as R2 to 4.4.4.4. It can ensure that the distance from R3 to 4.4.4.4 is less than the distance from R1 to 4.4.4.4. We don't need to switch it accordingly. The reason why the serial port is used below. It's because I want this line to be the only one in this picture. Certainly. The lower part can also run the Ethernet port. It's okay. Now we actually rarely see such a network topology. Generally speaking, it can also be all Ethernet ports. This is more common. For now, I just need to ensure the distance from R3 to R4 equal to the distance from R2 to R4 is okay. Then we change it to R2. That is, now I put the bandwidth and delay in the right interface of R3. Change it to be exactly the same as the right interface of R2. Then their calculated AD is the same. These two paragraphs are actually equivalent relations. As long as the parameters of the two interfaces are consistent.